Hi, good morning, everyone. Cool. So welcome back to ME 380. And first of all, I would like to go over the question we left it behind in the previous lecture. So we have a crank slider. Let me draw the diagram again. So I ask you to think about case number 3. What if we have gravity in the system and then we want to use energy method to find the driving torque of the system? Okay. So in order to use energy method, the first thing is you need to find the total energy E of the system. So for E, you have two components, kinetic energy and potential energy. So in previous steps, we already know that the kinetic energy has both linear part and rotational part. J2 theta 2 dot square. And then, so we need to calculate kinetic energy for each moving link. So link number 2 is moving, number 3 is also moving. Oops, that is J3 theta 3 dot plus, and then the last one is very special because the number link number 4 is a slider. So there is only linear motion, no rotation. So that's why we ignore the last term. So how about the potential energy then? Because in here, as I said before, in order to calculate a potential energy, in our lecture, we only focus on gravity and spring. So in this case, there is no spring, but we do have gravity. So we need, first thing we need to do is we need to find where all these gravity are applied. So we have one gravity force. We name it as, let's name it as F2. This is F3. And then that's F4. So that's the gravity force due to associated with each link. And then in order to find the potential energy, we just find the potential energy for each link. And because, as I said before, in order to calculate potential energy, you need to find a reference point because potential energy is a reference, is a relative energy. So you can pick your favorites. You can either pick these line, this flat horizontal line as U equal to 0, or you can pick this line as U equal to 0. Okay, so in this example, I'm only gonna pick the bottom line. So after class, you can actually choose the top line. That should give you the same result. So U equals to the gravity times the distance, right? Theta h2. So this distance is the distance of your center of gravity away from the reference line. So in this case, your center of gravity is d2. So which means this red line is going to be a theta h2. The same way, this height is going to be your theta h3. Okay, so we have two components, F3, theta h3, and then the last one is a mass sitting on that slot. So we have F4 times the total height of your of the rail. We also call it offset. So that's C. C is a constant offset. Okay, so that's the total potential energy. So then we need to find what these theta h2 is. So theta h2, if you look at the triangle, so we have your O2, G2, and then this angle is theta 2. And we need to find that edge. So according to the geometry relationship, so this theta h2 is just half of the length times sine theta 2, right? And then we can calculate delta H3. Delta H3 is kind of tricky. So you actually have two ways to calculate it. So let's recall where the theta 3 is. We define the theta 3 in this angle. So not all these data edges can be calculated easily from this geometry relationship. If you have like more than one link involved in the path, then my suggestion is go back to your displacement vector. So you need to find the displacement vector for center of gravity. Center of gravity G3. Okay, that's our G3. So the displacement vector is starting from your reference line. So your reference line is O2. It ends at the point you want to calculate the potential energy. So that's your G3. And then we already know that, let's name this point joint as A, is a summation of O2A plus AG3, right? And then we already know that O2A is just A times EJ theta 2. And then AG3 is half B EJ theta 3. But then we define the theta 3 at the joint B. So we need to reverse the direction of the vector. So that's the total O2G3 displacement vector. So data H3, which is the y coordinates, so which means we need to find the imaginary part of your O2G3 vector. And then we can write it down as A sine theta 2 minus half B sine theta 3. All right. So up to this point, we find all the U, find all the total potential energy. Your potential energy U equal to gravity of link number 2. That's M2G times half A sine theta 2 plus M3G A sine theta 2 minus half B sine theta 3 plus M4G C. Okay, so that's your potential energy. And then your kinetic energy is always the same, no matter if you consider gravity or not. So you have T and U. And then in order to calculate the input torque, we know that the input torque times theta 2 dot, that's the input velocity. So these two together give us the power generated by external excitation. So depending on how much power you generate, y is minus instead of positive, okay. That's because your AG3, let's label this AG3 vector out. I'm gonna use a purple color. So your AG3 is this vector, right? But then our theta 3 is defined around point B. So your BA vector, by definition, is BEJ theta 3, right? And then if you look at AG3 vector, is half of the AB vector, right? Because your G3 is in the center. Okay, cool. So you have the freedom to choose a theta 3 in the future. So just pay attention. You have to keep in mind where your theta 3 is aligned. So any power, so let's continue talking about these. So any power generated by external excitation is going to change the total energy in the system. So this power equals to the changing rate of the total energy. So that means dE dt, that's the changing rate. So the kinetic energy is changing the potential energy is also changing, right? So dt, we already calculated these for the very first case, somewhere over here. Yes, that's it. Because in the very first case, we assume there's no potential energy or no gravity. So your dE dt directly equal to dt dt. So you can directly copy and paste this and then put it in here. And then the next step is we need to calculate what the du dt is. When you want to calculate time derivative, you need to find all the time dependent variables. So your mass is constant, gravity is constant, length is constant, your theta 2 is changing, and theta 3 is changing, right? So that means you only need to calculate time derivative for these angles. So let's focus on the first one. It's m2g half a, sine becomes cosine theta 2, and then one more time derivative. The same thing applies to mg3g, a cosine theta 2 dot, minus half b cosine theta 3 dot. So the last one is special because the slide is moving along a horizontal line. So that's why your c is constant, everything is constant. So that's why the last term becomes 0 after doing time derivative. Okay, so let's focus on this du dt. So it's only related to position and velocity. As we mentioned before you're doing any force analysis, we already completed velocity acceleration analysis. So that means all these terms are known values, and then dt dt is also known. The only unknown in the system is your input torque, and then you can calculate that easily using only one equation. All right, makes sense? All right, cool. So let's move on to lecture 16, I believe. Yep. Oops. So first of all, I think I missed one important known value. I forget give you the theta 2 dot. That's 0.4 pi radian per second. So please write this down. So only this number can give you these position, velocity, and acceleration. Okay. So here we have a 4-bar linkage. That's a general form. And we know that it's made of steel. And then we know the dimension of each link. So you can easily calculate the moment of inertia and mass. So let's name it as M2, J2, M3, J3, M4, J4. And then in this example, we ignore gravity. But then I believe in the homework 5, I ask you to consider gravity in the system. Okay? So how can we find the torque? Again, you have two methods. The first method is always Newtonian method. So in order to find the Newton equations through Newton's second law, you need to find the free body diagram first. So actually, it's very similar to the crank slider system. The only difference is your link number 4. Your link number 4 in this case is a link, it's not a slider. So that's why for link number 1, you still have 2 reaction force, and then you have an input torque. And then for that's link number 2. For link number 3, you only have 2 reaction force. Go to A, B. There's no torque at all. But then for link number 4, that's the major difference right now. You have your reaction force at joint 04 and reaction force at joint B. Okay. So again, for each link, you're going to have 3 equations, right? 2 equations from linear motion, 1 equation from rotation. So 3 equation here, 3 equation there. If you compare these free body diagram with the crank slider free body diagram, they're actually identical. So that means you can directly copy the first 3 equations from previous lecture. So I'm not gonna go over that again. So I'm gonna use link number 4 to refresh your memory. So first of all, we need to label these reaction force correctly. So as I said, we use 2 index and actually 3 index to label each reaction force. So this one is going to be 1 for X, 1 for Y. That's 3 for X, 3 for Y. That's link number 4. So it always, the first index indicates where the force is coming from. The second one indicates where the force is applied. That's link number 4. And then X and Y indicates the direction. And then we find out the center of gravity, J4. So most of the time we assume your link is homogeneous, but we're gonna discuss what if your link is not homogeneous, if your G4 is actually away from the center. We're gonna discuss that later. So in this case, your G4 is at the center. So again, we should have 3 equations there. So what are these equations? So first, definitely linear equation along X direction. So you just sum all the X direction force. And then these forces together is gonna generate a linear acceleration along X direction. Same thing, Y direction. You just put all the Y direction force together and it's gonna generate a, oops, that should be 4. Y-axis acceleration. And then you have rotation. Remember that when we write these linear equations, so is the reference point is G4. So the rule of thumb is we pick the center of gravity as a reference point to calculate linear motion. So if that's the case, you always pick the same reference point to calculate your rotation. That's very important. All right. So then again, we have T34 plus T14. That's going to generate a angular acceleration. And then we know that T34 is a torque associated with F34. And then T14 is a torque associated with F14. Okay, so your T34 is calculated from a cross product. We need to find the position vector, cross product, your force. And then what is your position vector? So R34 which means it always starts from the reference point, and then it ends at where the force is applied. So in this case, that's going to be your R34. And then for the second displacement vector, it starts from the same center, it ends at here, so that's going to be your R14, okay? So let's see, so your R34 vector is actually half of your O4B vector, right? And then let's recall how the theta 4 is defined. I believe the theta 4 is defined around O4 point. So that's your theta 4. So which means it's directly half C E J theta 4. So let's assume, is there a place? Okay, let's name this as length A, this is length B, this is length C, okay? The length of the link number 4, oops, where is it? The length of the link number 4 is C, so that's why it's half C. And then you just calculate the cross product. You lay out them in a row. So you have F3 for X, F3 for Y, 0, and I, J, K unit vectors along X, Y, Z directions. And then by definition, it's just R3 for X, F3 for Y, minus R3 for Y, F3 for X. And then we just need to find the X component and Y component for these vector. So basically, that's the real part of your R34. That's the imaginary part of your R34. Okay, so that's how you find your T34. The same thing, you can find your T14. As I said before, you just replace R34 index by 14 because they're in the same format. All right. So that's how you get 3 equations from link number 4. You can see that actually generalized 4-bar linkage is even simpler because we have 3 identical equations similar to the previous 2 links. All right. So any questions? Okay. So that's a very special case, and we ignore gravity. So if you want to use energy methods, you just find all the total energy of the system, right? So because we have 3 rotating links, so your total energy E equals to T plus U is always the same. And then we ignore gravity. There is no spring force. So in this case, your E is directly T because of no gravity. Okay, that's the only reason why you can ignore gravity. All right, so we need to find the total kinetic energy. So again, your kinetic energy is T1 plus T2 plus T3 plus T4. You just find the kinetic energy for each link. Your ground link is not moving, so that's why the first term is always 0. So your T2 equals to T2 linear plus T2 rotational. When we talk about kinetic energy, it's both linear motion and also rotational motion. Linear motion is half m2 v2 amplitude plus half inertial times theta 2 dot square. So as I mentioned before, if you don't want to put your absolute value symbol in the expression, you can write these as dot product of 2 vectors. So that actually helps you when you calculate time derivatives. And then the same way, you can find your T3 and T4. Just replace the subscript from 2 to 3 and 4 respectively. All right, so because again, after doing velocity and acceleration analysis, everything on the right-hand side is known. So we can easily calculate E dot, which is the changing rate of the energy. We know that that should give us that should equal to the power generated by the external excitation. So you only have T input as your unknown. Everything else is known. So you can calculate your input. All right. So force analysis is actually, I think it's actually easier than acceleration and velocity analysis because it's just a lot of copy and paste. You have to be patient and you be careful when you make calculations. So that's case number 1. So again, I want to make slight changes to these example, case number 2. So let's focus on these 4-bar linkage again. That's your A, B, and C, O2, A, B, O4. So my question is, what if we have a spring K connected to the wall? Or I think that might be a little bit tricky. Let's change the spring as like a constant force. That might be easier. So what if we have a horizontal force applied? F is horizontal. Can you find the driving T input? Yeah, if it's a spring, definitely you can calculate that, but then I have to make a lot of assumptions. You might get confused right away. We have assumed that spring deformation is always flat, is always horizontal, and I have to give you an initial position for the spring. So perhaps we can discuss that. I can give you another case after this, but then I want to keep these, change these to a constant force F, which is horizontal to the negative side. So actually in these guys, the easiest way to do it is using energy method, right? So if you use energy method here, let's only discuss energy method. Okay, so look at the energy method. As I said before, the changing rate equals to the power generated by external excitation. I should put a plural there. It might be more than one excitation. Okay, so do we have to change the E dot term? We only add one force, right? So this force is not gonna change your kinetic energy description, right? So that means your E dot is still gonna be the same. But then we have one more external excitation. So the first one, we already know that is T input dot product theta 2 dot. So how about the F? So your F should be F times velocity of the point B, right? F is the vector. That's the definition for power. Yeah, if force is known. Yes, this force is known. Your force is horizontal and then is known. So because we only added external excitation, so we still have these torque input, but we have another force input. And then your force, we already known. We just need to find the point, the linear velocity at point B, right? So that's actually simple. So in order to find your point B velocity, you just find the reference for B vector, right? Start with the displacement vector for B, and then that's actually C E J theta 4. This is your theta 4. And then we know that your VB is J theta 4 dot C E J theta 4. Okay. And then we need to calculate the dot product. So your force vector is, if you want to add a minus F, or right, because it's to the left. The F is the amplitude of the force. So it's to the left, so that's why it's negative. There's no Y component. And then we need to find the VB vector. So the first term is the real part. So that's going to be minus sine theta 4 C theta 4 dot. And then the second one is going to be the imaginary part. So that's cosine theta 4 dot C. And then what you do is you just multiply the entities one by one. So F vector dot product VB vector is the first X entities times minus sine theta 4 C theta 4 plus 0 because you have a 0 here. So that gives you a 4F C sine theta 4 dot. Make sense? Then if you don't, so we can actually quickly check if it makes sense or not. You can see that E dot at that position is a constant, like is given. And then these FC times sine theta 4 times theta 4 dot, because theta 4 dot is rotating counterclockwise. So that's why it's positive. Theta 4 is between 0 to pi. That's also positive. C is positive. F, because the amplitude is positive. So that means the work done by your F is actually positive. That's at this point, your E is almost like a given value. So we give it a positive power. That means we need less input torque to drive the system. And then if you look at the physical system, that actually makes sense, right? You have a torque rotating counterclockwise, and then the force is actually pushing towards the same direction. So that's why you need less torque. That's another way to quickly check your solutions. All right, make sense? Okay, so that's case number 2. I can make a lot of changes. So in the exam, I might make a similar change like that. So your case number 3 will be, okay, let's focus on the same link. 2, 3, and 4. Okay, so in this case, we also ignore gravity. But then I can say that, okay, when we design the link number 4, we are not using a homogeneous bar. So we actually design the bar such that your G4 is away from the geometric center. Okay, so that's your O4, that's your B. I can give it a random number. We can say BG4 equals 1/4 of the total length. Let me write it more clearly. BG4. All right. Can you find the driving torque T input? So let's first talk about Newtonian method. Newtonian method. Again, in order to use Newton's second law, we need to find the force diagram or free body diagram. And shifting these G4 upward doesn't change the free body diagram for 2 and 3, right? So that's why you can directly use the same equation. The only thing we need to change is your O4 link. Is your fourth link, J4. Okay, so we have the same reaction force, 1 for X, 1 for Y, 3 for X, 3 for Y. So along X axis, you have the summation of all these forces. That's going to give you the acceleration along X direction. For the Y axis, similarly, summation of the Y components generates a linear acceleration along y. But then remember, your linear acceleration is reference. You need to refer back to your G4, which, remember, this G4 is always the center of gravity when we talk about equations of motion. You don't pick the geometry center. You're picking the center of gravity, okay? So then we have another rotation. Again, your rotation is about center of gravity, not geometry center. So you have T34 plus T14 equal to J4 theta 4 dot double dot. And also you need to remember your J4 is calculated about G4. So in that way, let me see what's the best way to say it. I think to save your time, I'm going to provide your G4 if I do shift the center of gravity away from the center of geometry. So you don't have to worry about the physics in your exam. So let's directly assume this J4 is already known. So what changes we need to make to accommodate these center of gravity shifts? So we need to change your linear acceleration. We need to change the torque expression, right? And then actually J4 needs to be changed, but then I'm gonna take care of that for you. Okay, so how about A4X? So your A4X always starting from displacement O4 G4, because we know that this is 3/4 of the total length. That's 3/4 of C EJ theta 4, right? From displacement, you can get a velocity. That's your VG4. It's just one time derivative, CJ theta 4 dot EJ theta 4. And then you have your acceleration, AG4 vector. Just one more time derivative. That's 3/4 CJ theta 4 double dot EJ theta 4 minus 3/4 C theta 4 dot square EJ theta 4. So that's how you get your acceleration at center of gravity. It's going to be a vector, but then the x component is the real part of this vector. Same thing, the y component is the imaginary part of the same vector. So that's how you make changes to your linear acceleration, because it's no longer at the center of geometry. You have to make these changes. And then the same thing, you need to find your new T34. The torque 34 again is R34 displacement vector, cross product F34. And then we have to go back to the definition. This R34 is a position vector. It starts from the center of rotation, starts from J4, and it ends at where the force is applied. So in this case, is B. So that means it starts from the center of gravity, goes back to a B point, okay? So that's your R34 vector. So this is your R34 vector. So your R34 equals to G4B, which is 1/4 of the total vector O4B. So that's why it's 1/4 C E J theta 4. So in this case, when you want to calculate the second torque, T14, you cannot directly copy and replace the index. You have to go back to the definition again. And then calculate them using cross product. So your R14 vector, let's find out where the center of gravity is. So it's same G4. The force is applied at O4. So that's the vector you need to find out. So it's really hard to find a G4, O4, but if we reverse it, then it's relatively easy because that's 3/4 C E J theta 4, and then there's a minus sign in front. Okay, make sense? So the trick here is when your center of gravity is not at the geometry center, you might need to do more calculation. You cannot directly replace the index. You have to go back to the original definition again. Okay, so if you understand, let me see. Yeah, if you use energy method, I forgot to mention one thing. Okay, if you're trying to use energy method, because there's no gravity, right? So E is T2 plus T3 plus T4. So you can copy and paste your T2 and T3. The only thing is your T4. Your T4 is half J4 theta 4 dot square plus half M4 V4 vector dot product V4. So that means your V4 has to be changed as well. Your V4 is no longer the velocity at the center of geometry. It's actually the velocity. Let's name it in a different way. It's actually the velocity of these G4 point. Okay, so that's why you have to go back to when you calculate your V4, you have to start from the displacement vector O4 G4, and then your velocity is actually dO4 G4 dt equals to V4. And then if you recall, that's 3/4 C E J theta 4, and then that's 3/4 C J theta 4 dot E J theta 4. Just keep in mind, when you calculate energy, the velocity, linear velocity is the linear velocity for the center of gravity. The rotational energy is a rotation about the center of gravity. So it has nothing to do with center of geometry. Okay, so that's the energy method. And if you understand case 2 and case 3, then I believe you can handle the project number 3. Let me go back to project number 3. So that's our project number 3. Is a 4-bar linkage. You saw this before in position analysis and velocity analysis. But in this case, I'm going to give you a T force at point P. And then we need to find out what is the input torque, T input at joint O2. All right. So first of all the links, they're no longer rods, but then they have a cross section of, they have a square cross section. So it's like 50 by 50, the length, the cross section is 50 by 50, and then the total length is given respectively. So that's the geometry. And then this triangular coupler is actually a plane with a uniform thickness. I try my best to draw it out. Okay, that's it. That's your point, joint A, that's your joint B, that's your joint P. And then the thickness is also 50 millimeter, okay? You can easily calculate the volume of each link, and then based on the density, you can calculate the math. All right. The real challenge is actually the triangular shape. I'm going to give you some hint. Let's look at these triangular shape, A, B, and P. If you want to, let me write it down somewhere else. I need a lot of space. Okay, here we go. I'll draw it again. A, B, and P. Okay. So if you want to use Newtonian method, then you need to draw a free body diagram for these triangular shape. And then how much force we have? How many forces we need to put there? Definitely there is a downward force F, right? And then we have two joints, A and B. If there is a joint, you always just put two forces there. One along X, one along Y. And then this is from link number 2 to link number 3, 2 to 3. This one is from 4 to 3, 4, 3, Y. Okay, typo. That's relatively easy, right? The free body diagram. And then if you remember, we need to find the X for link number 3. We have X direction. You just sum all the X component together because your P point force is always vertical, so there's no horizontal component. That's going to give you a linear acceleration along X. Same thing, if you sum all the Y directions together. In this case, you have to consider the P point force, and then it's negative, so that's minus F. And then you have M3A3Y. And then you have your J3, theta 3 double dot equals to T23 plus T43. You also need to consider the TP, which is a torque introduced by P. And then going back to the definition or our previous assumption, these linear accelerations and then all the torques, they're calculated around G3. Oops. That's the center of gravity. So where's the G3? Do you have any ideas how to calculate it? It's not a right triangle. So it's not as simple as the lecture 14. Well, the easiest way is actually using SolidWorks. You just draw this geometry in SolidWorks, and then you assign a density to this triangle. And then I believe there is like a feature in SolidWorks called mass properties. I might remember the name wrong. Yes, by definition, the center of gravity is the intersection of these midpoint lines. So let's say that's your midpoint of AP. That's your point of midpoint of BP. So that's going to be your G3. Mathematically, you can calculate your G3. So that means if your coordinate for A is AX, AY, coordinate for P point is PX, PY, That's bx, by. So your G3 is going to have a coordinate of this. So that's based on a homogeneous plane. That's when I say the density is uniform in that triangle. So that's how you can do it. But if you have a really weird density distribution, the best way to do it is using SolidWorks. All right, so that's your G3. Once you find these points, can you find the linear accelerations at that point? So if we already give you this G3, can you find A3x? So you don't, in order to calculate the acceleration there, you need to find the reference point, right? Let's use O2 as a reference here. So by definition, in order to calculate acceleration, A3, you don't worry about anything, just start from displacement vector always. Your displacement vector is starting from a fixed point, O2. It ends at the point G3. And then it's really hard to get it in one shot, but then you can divide it into a summation. Make sense? And then your O2A is, you can write it either using AEJ theta 2, or you can write it as AX and AY, right? You can use the X and Y components. So your AJ3, by definition, so if you know the coordinates of the two end points, can you find the vector connecting these two? Yep, so it's easily G3x minus AX, right? G3y minus AY. Make sense? It's just the difference between the two coordinates. So that's how you find your AG3. So in total, you can find your O2 G3 vector. And then once you find this vector, you just calculate two time derivatives. And then the x component is your A3x, y component is your A3y. The next tricky thing is how to find your J3. I'm not sure if I give you these equation in lecture 14. Again, you can do this in MATLAB. Oh, sorry, you can do this in SolidWorks. I think I'm gonna give you this J3, okay? So, J3 will be provided. So keep an eye on the future announcement. I'm gonna give you the J3 and also give you the coordinates for G3. So then you have a better understanding. All right, so J3, I can handle this for you. But then how about these torques? They're also very challenging. So let's take this TP torque, for example. TP torque by definition is the position vector RP cross product, the force term. What is your RP vector? By definition, starts at center of gravity. So that starts at G3. It ends at where the force is applied is P. So that's why RP vector equal to J3P. So which means you start from J3, ends at P. So that's the RP vector you need to find. Can you find these RP? hopefully. Okay, so just go back to the definition. So your RP has two, you know the two ending points. You know the geometry, you know the G3 coordinate is G3x, G3y. You know the coordinate for P is PX and PY. So that means your RP is just the difference between these two coordinates, PX minus G3x, PY minus G3y. Okay, and then your RPX is directly calculated, RPY is directly calculated, and then you can do the cross product thing. So for project 3, you might need to get used to Cartesian coordinate again, because your G3 is not very convenient to describe G3 in a complex domain. Let me see. Let me see. Yes, definitely you can, but I'm going to give you a recommended coordinate system. So let's use these as theta 3, theta 2. This one as theta 3. This one as theta 4, which is similar to previous homework. I think that's also helpful for you, because then you can use the same code from previous lectures to do the velocity and acceleration analysis. Because when you calculate force, you need to repeat all the previous stuff again. So my suggestion is use the same coordinates in previous homeworks, and then just use the existing code. So you don't want to mess up with those acceleration and velocity results. All right. So let me know if you have any questions about project 3. I think you have plenty of time to finish it. I think the deadline is May 3rd or May 2nd. And then in the first two parts, you just need to calculate the torque at the given position. The last part, you need to find the torque as a function of the input angle. You can pick either method. So I believe the energy method is going to be much easier. All right. So that's it. That's the end of today. All right. Thank you, guys. Have a good one.